Every year, amputees traverse thousands of miles in an effort to find a replacement for the irreplaceable. According to the Amputee Coalition of America, there are approximately 1.7 million amputees in the US alone. As any doctor knows, the arm and leg are two amazingly complex pieces of machinery that most of us take for granted. After the loss of such a vital part of the body, many amputees begin the search for a suitable prosthetic limb, all the while spending tens of thousands of dollars on semi-functional lookalikes. In order to provide a sufficient limb replacement, the most effective solution would interface directly with the brain itself, which is possible today using electroencephalography. Electroencephalography, or EEG, relies on electrical potential generated in the brain by synapses between neurons, and uses these signals to provide an approximation of the user's thoughts. Normally, in order to analyze signals produced by an EEG, it first goes through several stages of extensive signal processing and filtration, data classification, and user training. However, I also learned that EEG is deemed inapplicable in such real-world problems due to the need for a more accurate, robust, and easy-to-use interface. My project sought to rectify this through the improvement of existing EEG signal processing software. To do so, I created two custom scenarios in OpenVibe, a widely used open-source signal processor, one for user training and one for real-time use. I performed two different tests, a simulation test and a live EEG test using signals gathered from my brain, and compared the pattern detection accuracy achieved with my scenarios with that achieved by the default OpenVibe BCI scenarios. I found that, by using vector quantization sampling methods using an algorithm I developed, and linear discriminant analysis to remove much of the unwanted artifacts from the data, I was able to increase the accuracy of detecting patterns by 15.5% during simulation and 12.5% during real-time use. My scenarios, despite putting a greater load on the CPU, were able to achieve a significantly higher positive pattern detection rate that could relate to a much easier training setup on the part of the patient. Although there was always room for improvement of the software through additional experimentation, I believe it is safe to conclude that this project demonstrated that it is possible for EEG technology to be applied in the field of prosthetics, and with implementation with today's robotic devices, could produce a practical brain-computer interface that could make amputation a thing of the past.